Third International Physics Olympiad, year 1969, IPHO. Problem number 4. A glass plate is placed above a glass cube of 2 cm edges in such a way that there remains a thin air layer between them. See the figure. Electromagnetic radiation of a wavelength between 400 nanometers and 1150 nanometers, for which the plate is penetrable, indicate perpendicular to the plate from above is reflected from both air surfaces and interferes. In this range, only two wavelengths give maximum reinforcements. One of them is lambda equal 400 nanometers. Find the second wavelength. Determine how it is necessary to warm up the cube so as it would touch the plate. The coefficient of linear thermal expansion is alpha equal 8.0 by 10 power negative 6 degrees Celsius. Interactive index of the air N is 1. The distance of the bottom of the tube from the plate does not change during warming up. Solution for problem number 4. Conditions for the maximum reinforcement can be written as 2dn minus lambda k over 2 equal k lambda k, for k equal from 0 to 1, 2, etc. Here, because we are losing half of wavelength due to reflection so we have this equation. But because n equal 1, we finally have 2d equal 2k plus 1 multiplied by lambda k over 2. So here we have d is thickness of the layer, and we assume that n equal 1 and k is maximum of order. Let us denote that lambda prime equal 1150 nanometers. Since for lambda equal 400 nanometers, the condition for maximum is satisfied by the assumption, let us denote that lambda p equal 400 nanometers, where p is an unknown integer identifying the maximum order for which lambda p multiplied by 2p plus 1 equal 4d. The equation yields that for fixed d, the wavelength lambda k increases with the decreasing maximum order k, and vice versa. According to the assumption that lambda p minus 1 must be less than 1150 newtons, but lambda p minus 2 must be greater than 1150 nanometers, we have this inequality, which can give us next inequality. We assume here that now instead of p we have p minus 1, and here we have p minus 2. Now substantiating to the last inequalities 4d, that we have these two inequalities. Here we have lambda p equal 400 nanometers and lambda prime equal 1150 nanometers. So we can subtract everything by 400 nanometers and we have these two inequalities. Now we can count both separately, that from one hand we have p must be greater than 31 over 30, but from other hand it must be less than 77 over 30, and both of them give us p equal 2. And now we can denote that lambda 2 equal 4d over 5, which is 400 nanometers, and from here we can find that total length d equal 500 nanometers. Now we can find what are lambda 1 and lambda 0. For lambda 1 we have that's equal to 4d over 3, which is 666.7 nanometers, which is good because it's less than 1150, and lambda 0 equal 4d over 1, which is 2000 nanometers, which is greater than 1150. It means that we solved this problem, because next maximum will be for 666.7 nanometers. And last thing is to find what is change of our temperature, because total dL equal alpha multiplied by L multiplied by delta T. Here we have a delta L equal 500 nanometers. Alpha, that's our coefficient of enlargement. L is our 2 centimeters, and delta T we have to find. So that will be delta L over alpha L, and after putting numbers we have 3.1 degrees Celsius. That was a full solution for problem number 4.